Have you ever had that feeling, like when you're really trying hard to wrap your brain around how these super advanced AIs actually work?
Yeah.
It's kind of like you're staring into this black box, right? You can see all the amazing things they can do, but what's actually going on inside,
Right.
it feels totally mysterious, like magic almost.
It does.
Well, today we're going to take a deep dive into a new area of research that's trying to do just that, shine a light inside that black box.
Okay.
It's called mechanistic interpretability. And we're going to be specifically focusing on a brand new method called circuit tracing.
Interesting.
So you can think of it as like trying to create this map of the pathways inside these giant language models.
Okay.
So we can finally actually understand how they process information.
That's a really good way to put it, yeah. Because, when we talk about these complex AI systems, their ability to actually, understand and generate text, it all boils down to these super intricate calculations happening across just as a massive network of artificial neurons. And the real challenge, like you said, is how to make sense of this whole web of transformations. Like, how do we make it understandable to us?
Exactly. And for this deep dive, we're going to be looking at this really cool research paper called Circuit Tracing, revealing computational graphs in language models.
Okay.
And it's from the Transformer Circuits thread.
Right.
Now, this research isn't about like making AI faster or even better at a specific task. It's not just about performance.
Right.
This is really getting down to like the nitty-gritty, the fundamental level of how these models take in information and then actually do something with it.
Mm-hmm. Yeah. Our goal today is to break down those core ideas behind this circuit tracing method. And we really want you to come away from this understanding what it is, how it works, and some of the really interesting insights it's already revealing. And we promise we'll try to skip all that super technical jargon and focus on the why, the how behind these impressive abilities that these language models have.
Perfect. All right. So to start off, these large language models, they use a huge number of artificial neurons arranged in these layers, right?
Yeah.
And when you give them some text as an input, that data, it travels through all these layers, and at each step, it kind of gets transformed and refined a little bit.
Right.
But here's the thing, with like billions of these connections going on, it's basically impossible to just look at the raw data and understand why the model produced a specific answer.
It's true.
It's just this incredibly complex, interconnected system.
Yeah, and that's why they're often called black boxes, right? Because even though they can do these amazing things, the exact way they transform that input into the output we see, it's hidden from us.
Yeah, we can't just see it.
You put something in, you get something out, and what happens in between, it's a mystery.
It's a mystery. And so that's where this idea of mechanistic interpretability comes in.
Okay.
This field is really all about making those hidden transformations understandable to us humans.
Right.
It's like trying to pop open the hood and see the engine. How do all these parts actually work together?
It is. And what's really cool is that mechanistic interpretability takes this two-pronged approach.
Right.
So first, it tries to find what they call features.
Okay.
And you can think of these as the model's internal building blocks, the reusable ones, the things that respond to very specific concepts or patterns in the data. And second, it tries to describe the circuits, which are the actual pathways that these features use to interact. And that's how they actually produce that output.
Okay, so the features are like the individual tools in a workshop, and the circuits are like the instructions for using them in a certain order to actually build something, to create that output.
That's a good analogy, yeah.
Now, how does this new circuit tracing method fit into all of this?
So circuit tracing basically introduces a whole new way to see these circuits in action for a specific thing you ask the model. So the main idea is to create a visual representation, a graph, that shows how information flows between these internal features as the model's processing a piece of text. And a really important tool they use to do this is something they call a replacement model.
A replacement model. That sounds interesting. What exactly are we replacing?
So with the replacement model, they're substituting parts of the original super complex model with simpler components that are easier for us to wrap our heads around. And for this research specifically, they focused on replacing multi-layer perceptrons, MLPs, which are like a fundamental building block inside these transformer models.
Gotcha. And what are they replacing those MLPs with?
They're using something called a cross-layer transcoder, or a CLT. You can kind of think of it as a translator that's been trained to mimic what those MLTs are doing. But it doesn't using a more understandable set of sparse features.
Sparse features.
Yeah, so sparse just means that for any given input, only a small number of these CLT features will actually activate. It's like finding just a few key pieces of information in a very noisy environment.
So instead of seeing this huge, complicated pattern of activity across all the original neurons, we get a much more focused pattern in the CLT, which hopefully is easier to understand.
Exactly.
Now, you mentioned that these cross-layer transcoders, they have features that can read in information from a specific layer, but then they can output to layers that come after that one. Can you explain that cross-layer idea a little bit more?
Sure. So a CLT is designed to have the same number of layers as the original model.
Yeah.
It's basically trying to understand, right? And for each layer in the CLT, there's this set of features. And each of these features takes information from what's called the residual stream
Okay.
of its corresponding layer in the original model. You can think of the residual stream as like a central highway where all the information being processed flows through.
Okay, the information highway?
Exactly. And this input is processed by a linear encoder followed by a nonlinearity, which in this case is this mathematical function called tan.
We don't have to go too deep into that.
No, the specifics aren't that important right now.
All right, so each CLT feature is kind of like listening in on the traffic on this information highway at its specific layer. But then what happens next?
So the key is that these CLT features, they're not limited to just influencing the very next layer. They can send their output, their own interpretation of the info they picked up, to all of the subsequent layers, and this allows them to capture complex relationships and dependencies that might span across many layers in the original model.
So a feature way back in an earlier layer could still potentially affect the final output of the entire model, even many layers later.
Exactly.
You also mentioned something called a sparsity penalty when training these CLTs. Why is that such an important part of the process?
So the sparsity penalty is crucial to making these features understandable. What it does is, during the training process, it encourages the features to become active only when they detect a very specific pattern or concept.
Okay.
This means that for any input you give it, only a small fraction of the total number of features will actually fire, so to speak.
So it helps us focus on the important ones.
Right. And that sparsity makes it much, much easier to figure out which features are really important for processing a specific request.
To give us a sense of scale here, I mean, they trained these CLTs on both a smaller 18-layer model and on the much larger Claude 3.5 Haiku.
Yeah.
And the total number of features ranged from hundreds of thousands to tens of millions.
Wow, it's huge.
That's a lot of potential building blocks.
It is. And training these CLTs, it can take a lot of computing power initially. But the idea is that it's worth it because it really improves our ability to understand what's happening. And they also point out that even simpler methods, like looking at the most active neurons, can give us clues. So it's a really rapidly developing field. And we'll probably see even better ways of doing this in the future.
That's really exciting. Okay, so we've got this replacement model, the CLT, with its focused cross-layer features. But how do we actually get a picture, a visualization of that computation happening?
Right, and that's where these attribution graphs come in.
Okay.
You can think of it as a visual map showing how much one feature's activation influences the others as the model's processing that text. So each feature is represented as a node in this graph, and the connections between them, the edges, show how strong that influence is.
Okay, so if there's a strong connection between feature A and feature B, does that mean that when A becomes active, it's very likely that B will become active as well?
That's exactly right, yeah. And because we can actually trace these connections, these attribution graphs let us follow the steps the model takes internally to arrive at its final answer. It's really cool.
Wow.
We can see which initial features are triggered by your input, how those then activate others in later layers, and so on, all the way to the features that contribute to the final prediction.
It's like we're finally getting that roadmap of how information flows through the model.
Exactly, a roadmap.
And I understand the researchers developed some pretty cool visualization tools to actually work with these graphs. I can imagine they get pretty complex.
Oh yeah, they can be very complex. So to make sense of them, they created interactive tools that let you explore the individual features, their connections, and how they're activated.
Yeah.
And of course, it's important to have ways to check if these graphs are actually showing us something real.
Right. We want to make sure they're accurate.
Exactly.
So let's look at a specific example. The paper talks about this case with an 18-layer model completing the acronym NDG for the National Digital Analytics Group. What did the attribution graph show us in that case?
So that example is a great way to understand how this works. The graph for the NDG prompt showed very clear pathways starting from each important word in the desired acronym. So digital, analytics, and group. And for each word, there were specific features that seemed to be about saying the first letter of that word in the correct position in the acronym.
So like a feature activated by digital that's responsible for saying D as the first letter, and then another for analytics saying A as the second, and so on.
Exactly, exactly. And these, say, X output features, they had positive connections to a more general, say, DAG feature, as well as direct connections to the final prediction.
So there were multiple paths leading to the same output?
Yes, there were sequential paths, but also direct links from the features associated with each word to the final prediction.
Now, the paper also mentions something called supernodes. What are those, and how do they fit into this NDAG example?
So because you can have many individual features that all respond to the same basic idea, like you might have several slightly different features that all fire when you see the word digital in various contexts.
Okay.
The researchers came up with the idea of these supernodes. They're essentially groups of related features that can be treated as one unit to make things easier to analyze.
So for digital, you might have a bunch of individual features that all become active, but for this particular task, they can be grouped together because they all have similar downstream effects.
Right, and this helped simplify the graph so you can focus on the bigger picture.
That makes sense. It makes the graph less overwhelming. So what other interesting insights did they get from the NDAG graph?
Well, there were also features that seemed to be related to the overall context. Like, there were features for in an acronym and in an N at the start of an acronym that had positive influence. So this suggests that the model actually understood it was supposed to be generating an acronym and that it needed to include that N that was already there. Interestingly, though, the word national didn't seem to have a strong direct influence on the final prediction.
Really?
Yeah, the researchers think that its role was mainly in influencing how the model paid attention to the other words. And that's something that this specific circuit tracing method doesn't fully capture yet.
That's a really important point, and we should definitely come back to the limitations of this method. But first, you mentioned an interactive interface for exploring these graphs. What can you actually do with it?
Oh, it's really cool. You can dig into the details of the graph. You can hover your mouse over any feature or connection to see more information about it. You can select specific parts to zoom in. The supernodes help manage the complexity. You could even rearrange the layout to try to find patterns. It's designed to be very hands-on.
So it's a way for researchers to really get in there and play with the model, see how it's thinking.
Yeah.
Now, how do we know if these attribution graphs are actually telling us something real about the model? How did the researchers test if this method was working?
Testing is super important, of course. One way they evaluated the replacement model was by checking how often its prediction for the next word matched the original model's prediction.
Okay.
And they found that as they made the CLT larger with more features, it got better and better at mimicking the original model.
So the more features, the more accurate it becomes.
Right, and importantly, these CLTs did better than simpler approaches, which suggests this idea of using sparse cross-layer features is a good one.
And for the attribution graphs themselves, how did they know they were showing something meaningful?
For the graphs, they use things like a completeness score and a replacement score. The completeness score basically tells you how much of the important stuff is actually represented in the graph. And the replacement score looks at how well the whole graph explains the computation from start to finish.
Okay, so those scores tell us how comprehensive and accurate the graph is.
Exactly. And to deal with the complexity, they also used a technique called graph pruning, which basically gets rid of the less important features and connections.
So they're simplifying the graph without losing the important information.
Right. And then they looked at how much they pruned and how it affected those scores, trying to find a good balance between making it understandable and keeping the essential information.
That makes sense. You want a graph that's clear but still accurate. And you mentioned something earlier called perturbation experiments to validate the graphs, right?
Yeah, perturbation experiments are super important. What they do is they deliberately mess with specific features or supernodes, either by making them less active or more active, and then they see how that affects the output.
So it's like a controlled experiment where they tweak the model and see what happens.
Right, and if the changes match what the graph predicted, then it gives us evidence that the graph is actually reflecting a real cause and effect relationship.
That's really clever. It's like poking the model to see how it reacts.
It is.
Now, all of this wasn't just limited to that small 18-layer model, right? You mentioned applying these methods to Claude 3.5 Haiku.
Yes, they also applied it to Claude 3.5 Haiku, which is much larger and more powerful.
And what were some of the key things they learned from that?
Oh, there are tons of fascinating findings. It really hints at how sophisticated these models are. For example, they found evidence of multi-step reasoning.
Multi-step reasoning, what does that mean?
So Imagine the model doesn't just know that Dallas is in Texas. It can use that knowledge to figure out that Austin is the capital of Texas.
Wow, so it's not just memorizing facts, it's actually connecting them.
Exactly. It's reasoning.
That's incredible.
They also saw what looks like planning in poetry generation, where the model seemed to identify potential rhyming words before even writing the line.
So it's thinking ahead, planning the poem.
It seems that way.
Wow, that's getting pretty advanced.
It is, and they found multilingual circuits, meaning it uses both language-specific and more abstract ways of processing information. They looked at how it does addition, which was different from the smaller model. They even looked at things like medical diagnoses.
Medical diagnoses, how does a language model do that?
Well, it seems to generate possible diagnoses internally, and then uses those to guide what questions it asks next.
It's like it's thinking through the problem like a doctor would.
It really is fascinating.
So it's not just about language, it's about thinking and problem solving.
Exactly. It's about higher-level cognitive processes.
What about when the model makes mistakes?
Right. So they also looked at how the model handles identifying entities and those hallucinations.
Hallucinations.
Yeah, where the model makes up facts that aren't true.
Oh.
And they found circuits involved in distinguishing between familiar and unfamiliar entities. And they think that problems in these circuits could lead to those hallucinations.
So it's like the model is getting confused about what's real and what's not.
Yeah, potentially.
They also looked at how it refuses harmful requests.
Right. They found a general feature related to harmful requests.
So it's like it has this internal sense of what's harmful.
It seems that way, yeah.
And they also looked at how certain prompts can bypass those safety mechanisms, those so-called jailbreaks.
Yeah, they were able to see how those jailbreaks work internally.
That's pretty important to understand.
It is. It's about safety and control.
What else did they find?
Oh, they looked at how well the model follows its own reasoning in chain of thought examples.
Chain of thought.
Yeah, where the model explains its reasoning step by step. They could see when it was genuinely following the steps and when it was just making up an explanation.
So it's like checking if the model is actually thinking or just pretending to think.
Yeah, that's a good way to put it.
They even looked at a model with a hidden goal.
Yeah, and circuit tracing helped uncover the mechanisms related to that hidden goal.
That's incredible. It's like we're getting this deep insight into the AI's inner world.
It is pretty amazing.
But as with any new method, there must be some limitations, right? What are some of the challenges they're facing?
Oh, absolutely. There are still some challenges. One is that it doesn't fully capture how the model uses attention mechanisms, which is a huge part of how these models work.
Right. Attention is how the model decides which parts of the input are important.
Exactly. And they use this example with Aunt Sally to illustrate this. A basic attention mechanism lets the model learn from the context, but the current method doesn't show why it focuses on Sally.
So it might show that Sally was predicted because it appeared earlier, but it misses the deeper reasoning based on the relationship between Aunt and Sally.
Exactly. We're getting great detail on how the neurons fire, but we're still missing the why behind the attention.
So it's good at showing how the main processing works, but the attention mechanism is still a bit of a blind spot.
You could say that, yeah.
What other limitations are there?
Well, there are also error nodes in the graphs, which represent inaccuracies in the replacement model. And sometimes those can be pretty prominent and obscure the real computation happening.
So it's like the map is a little bit blurry in some spots.
Yeah, you could say that. They're also working on understanding the role of features that aren't active and those inhibitory connections where one feature suppresses another.
Because sometimes not doing something is just as important as doing something.
Exactly.
And how about feature splitting? How does that limit what we can learn?
So feature splitting is when one high-level concept ends up represented by many different features. Like, you might hope to find one feature for during, but you actually find many different, say, during features, each activated in different situations.
So it makes it harder to see the big picture, the underlying concept.
Right. It's like trying to understand a car by
Yeah.
looking at thousands of features for each specific part.
It's too much detail. It's not the general concept we're looking for.
Exactly.
But they are working on addressing these limitations,
Right.
right?
Oh, yeah, definitely. They're developing ways to represent features in a more organized, hierarchical way. And they're finding better methods to account for attention mechanisms.
So it's a work in progress, but it's moving forward.
It is, and it's moving fast.
So for our listeners who might be wondering why all this matters, why should they care about understanding the inner workings of these models?
Well, the implications are huge. If we can really understand how these models work, we can build AI systems that are more reliable and trustworthy.
Okay.
We can identify and fix any biases, and we can develop more efficient and controllable AI.
So it's about making AI safer and more beneficial.
Exactly. And on a deeper level, it could even teach us about intelligence itself, both artificial and biological.
That's a really exciting possibility. So to wrap things up, what's the key takeaway from all of this?
The key takeaway is that circuit tracing is a powerful new way to look inside these language models and understand the building blocks and processes they use. We're getting closer to truly understanding how they work.
And what's one surprising fact or a thought that sticks with you after looking at this research?
What really struck me was that acronym example, even for something as seemingly simple as completing NDA, the computation is really complex. And if that's the case for a simple task, it makes you wonder what's happening in those models when they're doing much more advanced things.
It makes you wonder just how deep those hidden depths really go.
It does. And for those who want to learn more, definitely check out the full paper on the Transformer Circuits thread. You'll find more details, case studies, and those interactive visualizations. Understanding these techniques is going to be crucial as AI keeps developing.
It really feels like we're on the edge of something big here, unlocking the secrets of AI. Thanks for joining us for this deep dive.